Okay, now we're going to go through a few basic simulation models just to get our feet wet here before we move on to more complex examples like the grizzly bear and the loggerhead sea turtle. We're going to start really simple and we're going to move on to more and more complex yet still quite simple models here. It's often said that all models are wrong and some are useful, and that's often attributed to statistician George Box. And it comes into play a lot because it's true. All models are wrong. And we're always trying to balance between complexity and simplicity in order to make a useful model. And I will say that we're going to start really simple here, and it's really on the wrong side of the scale here. We're going to start off with really wrong models, but very simple models. And so let's get started. Make sure you have Insight Maker open. You've logged into your Insight Maker account. In each of these following examples, I will provide a link to an Insight Maker model. I will right click so that I can open the link in a new tab so I can go back and forth between the website and the Insight Maker model. So here we go. Let's load up this Insight Maker model. And like I said, this is so simplistic as to be so wrong that it is not even useful, but it's a good starting place. So let's imagine now we have a stock that represents a population of moose, and we have two flows, one representing the total deaths into the total births into the population, and the total deaths or the removals from the population. Now, the first step is, if you want to make any changes to these models, hit this Clone Insight button at the top. It's kind of a small button, but it should be there. Clone it. Say, yes, I do want to clone it. And then you have a model that is yours that you can work on and make changes to. So I recommend doing that every time you open a new model. Once you do that, we can just run it and see what it looks like. Just hitting this simulate button up here. Let's run it. And here we go. This is a simple model of population growth that you might immediately notice is not super realistic. A couple things we can do. Let's just get out of those results. Let's say we want to change the settings to run this simulation for 50 years. So all you have to do is go up to the settings button and change the simulation length, and we can run it for 50 years. Let's do that, and you can hit simulate, and now the model's running for 50 years. All right. And we can change other things about this model too if we want. We could change the total number of births to be 4 instead of 5. So just open up the equation editor. Again, there's just, if you hover your cursor over the births flow, you can just see this equal sign. Hit the equal sign and you can change the number there. Or if you click on the flow, you can change the number over here. You see that the flow rate is equal to 4. Let's simulate it. And we see that we're in a very special condition. This is where birth and deaths are equal. Inflow is equal to outflow. That's called an equilibrium state. That's all you feel free to play around with the model. You can change the initial abundance. You can change the birth and death and see what happens. But what I'd like you to do is to pause the video at this point and answer the question. You can go back to the main page here. We can see, so pause the video and take a minute to write down a response to this question. Is the moose model realistic? Is this model realistic? I've already given you kind of the answer there that it is not realistic. What is the first thing you would like to change to make the model more realistic? So just take a moment to answer the short answer question within Web Campus and then come back to the video. All right, the next step is to build another layer of realism into this super simple model. And what we're going to do here is, instead of treating the birth rate as constant, a constant number of births every year and a constant number of deaths every year, which was super unrealistic, we're going to treat the number of births as dependent on the population size. So if every individual in the population gives birth to 2 offspring, we can multiply the total population by the total per capita. Per capita meaning in Latin per head, but basically per capita just means per individual in the population. We're going to multiply the total population by the per capita birth rate. And just the same way, we'll model the total deaths by multiplying the total population by the percent death rate each year. All right. All right, so click on the link to load up this model with per capita vital rates. I'll right click and open a new tab so I can go back and forth between the lecture and the Insight Maker model. And the model should look something like this. We see these variables on our workspace. Our variable you can add, and it just looks like this round oval. And it generally stores constant numbers for our population. Here we have a birth rate, which we've set at 0.5, and we have a death rate, which we've set at 0.4. And again, we have a stock representing a collection of individual moose, and we have a births flow representing the addition of moose into the population, and a death rate representing the subtraction of moose from the population each year. And we can just look at the equation that goes in here. To get the total number of births, we just multiply the total number of moose in the population by the per capita birth rate. And just the same way, to get the total number of deaths, we use this equation. We multiply the total moose population by the fractional death rate. And if we hit simulate, well, here, before we do that, let's clone this Insight so you can make changes to it. All right. And you can run it, and you see now that we get positive exponential growth. And if we were to run this even longer, let's run it for 200 years. We'd get very high numbers. Now, by the end of 200 years, we have 1 times 10 to the 10th power of moose, which is not a million, not a billion, but 1/10 billion or something like that. Anyway, that's a lot of moose. So that's what exponential growth can do. Given time, it will take over the world. All right, so going back to the lecture, we can ask a couple of questions. What happens if you set the birth rate equal to the death rate? What happens if you set the birth rate less than the death rate? And so if we go in and try that, let's go back to our clone here. We can try that, and let's set the birth rate equal to the death rate. So that's 0.4. So we'll have to set the birth rate at 0.4 and see what happens. And clearly that means the birth and the death, the total births is equal to the total deaths each year, and therefore we're in equilibrium state. All right. And if the birth rate is less than the death rate, 0.3, then we get a declining population. And that is called negative exponential growth. And the population eventually goes extinct. Now, there's a very important parameter in population ecology called little r, or the intrinsic rate of growth. And it's just computed as the birth rate minus the death rate. If little r is positive, the birth rate exceeds the death rate and the population exhibits positive exponential growth. If little r is negative, then the death rate exceeds the birth rate and the population exhibits negative exponential growth. So play around with it. This is just a basic exponential growth model and introduces a very basic concept of population ecology. But what do you say? Is this model realistic? Probably not. And so what's the next thing you'd like to change to make this model more realistic? You don't have to answer this in Web Campus, but just think about it. It's there's a lot of other elements that could make this model more realistic. You might want to think of a population, a real population that you're interested in. What other factors might come into play here besides just per capita birth rate and per capita death rate? There's a lot of correct answers there. All right. So one of the elements of realism that we would want to add potentially is uncertainty. Let's look at these two figures and think about which is more likely to represent a real wild population. This figure or this figure? Again, this one or this one? Which one's more realistic? Now, if you answered this one, you're right. More like if you look at data from real populations, they tend to go up and down, they tend to fluctuate in what looks like kind of a random way. They don't look smooth. They don't look like that. So what is it about this that makes it more realistic? It's just the fact that we just can't predict necessarily what's going to happen in one year or the next. There's fluctuations, and those fluctuations can be unpredictable. So that introduces a concept that we call stochasticity. So first of all, wild populations do fluctuate over time, and those fluctuations are often not tractable. We can't figure out why they happen, but they do happen. So to introduce realism, we have to acknowledge the fact that populations are like that. They fluctuate. They go up and they go down, and it's not predictable. The future is therefore uncertain. We don't know what the future is going to be, and that probably makes intuitive sense. But what do we really mean by that, and how do we model it? How do we include that in our models? So if you were to run the basic population model we just made, how many different results would you get? Well, you could try it. Let's make a positive growth model. Let's go back to 0.5 and 0.4 for the death rate. And we can simulate it, and we get exponential growth. I still have it running for 200 years, but every time I run it, it would look exactly the same. There's no difference from one run to the next. And that, by definition, means that this is a deterministic model. It means that we know a priori what's going to happen, and every time we simulate, it's going to look exactly the same. That's called deterministic. And the opposite of deterministic is stochastic. And stochastic means random. So ecological systems have inherent variability. We can't predict with certainty whether a single individual will mate or die. For each individual is different. We can't predict which individuals will live or die oftentimes. We can't predict if an individual will have triplets or quadruplets or won't be able to reproduce at all. A lot of this is unpredictable. We also can't predict whether this year or the next year or the year after or the year after that is going to be a good or bad year for survival or offspring production. So what do we do about this? How do we include this type of uncertainty in our models? As population ecologists, we do have some tricks for dealing with this. I like to think that we are able to embrace the uncertainty. It can be scary to not know what the future might look like. As a modeler, we're trying to give answers to managers, to stakeholders. We would like to give answers, but we also want to be honest to them. And we need to acknowledge the uncertainty. We need to acknowledge that the future is unpredictable. So how do we deal with it? Well, we deal with it using stochasticity or using random number generators. So when we include at least one random number generator in our models are called stochastic models. So They're models with random processes. And one of the things that are going to happen, and we'll see how this works, is that every time we run the model, it's going to look just a little different. So my model is going to look different from your model, and then the next time I run the model, it's going to look different from the time before. We can then interpret not just a single run of, say, 50 years in this case. We have to interpret a whole bunch of runs at the same time. So it's very convenient to overlay all these possible futures. Each one of these scenarios represents a possible future for this population. Perhaps it's going to grow. Perhaps it's going to get up to 200 after year 50. Or perhaps it might go extinct. And we don't know because inherent variability that we can't predict. And it's really useful to be able to acknowledge that in our models and to be able to run the model many, many, many times and to interpret this whole cloud of possible futures rather than just a single trajectory. We call one of these a single trajectory. Here we run 50 trajectories or 50 replicates. And we notice we can actually count up the number of times that a replicate went extinct. So out of 50 times, we had 1 extinction, 2 extinction, 3 extinction by year 50. So we have 3 replicates out of 50 went extinct. So please pause the video and go to Web Campus and answer this question. What is the extinction risk for this population? So can you compute the extinction risk? And then, this is more of a thought question and there really isn't a right answer, but just try to think about this and write something down. Is this extinction risk acceptable? What does it mean to be acceptable? Extinction risk. All right, so pause and answer the question on Web Campus. All right, so before we run our first stochastic model, I just want to say a few words about random number generation. So we're now going to start adding random number generators into our models. A random number generator is kind of like this lottery ball. It's just a bunch of possible numbers, possible values that you can shake up and draw one value randomly out of this and then put it back, shake up the lottery ball again and draw another number. There are several distributions of random number generators that we use as population ecologists, and I'm not going to go through those distributions right now. If you're in my class, you probably know a thing or two about these different distributions, but if you'd like to learn a little more about the distributions that we're going to be using, you can scroll down to the bottom of this lecture. I included a whole bunch of extra materials, a lot of it drawn from my population ecology class. So if you'd like to get some more details about random number generators, feel free to scroll down, but I'm not going to go through that right now. Instead, what I'd like to do is go back to Insight Maker. And we're going to add stochasticity into our models. And specifically, the first model we're going to include, we're going to play with, uses a type of stochasticity we call demographic stochasticity, which when we say demographic stochasticity, we're talking about the fact that we just can't predict which individuals will live or which individuals will die, which ones will give birth to triplets, or which ones will fail to give birth. This is what we call demographic stochasticity. To explore this model, let's click on this link, and I like to open a new tab. And like always, I'm going to clone this insight. Clone it. All right, so this looks very similar to a model we've already looked at, but if you click on this equal sign, you now see that the total births is now a random number generator. It's using a distribution called the Poisson distribution, and the total deaths is also sampled randomly from a distribution we call the binomial distribution. So that's the only difference in this model from the last one. We still have a per capita birth rate of 0.5. We still have a per capita death rate of 0.4. So nothing's really changed here. And in fact, throughout the whole simulation, we might see that there's some variability every time we run this because we have random number generators in this model, but the birth rate does not change. The birth rate stays constant at 0.5, the death rate is constant at 0.4, and the intrinsic rate of growth, which is the birth rate minus the death rate, is equal to 0.1. So there's nothing changing in the vital rates. So let's run a simulation, and let's make sure it's running for 20 years. There you go. And let's run a simulation. Now, if you ran a simulation, it probably looked a little different. Let's try it again. Well, it doesn't look that different. That one looks a bit different. So every time you run it, it should look a little bit different because now we have, this is a stochastic model, and by definition now, every time we run it, it'll be a little bit different. All right. One useful thing now, since every run is going to be a little different, we can't really interpret the results from just a single run. So now we have to make a whole cloud of possible futures, and we have to interpret that whole cloud. And so Insight Maker provides a nice tool for doing that. It's called the sensitivity testing tool. So if we go up to tools, go to the sensitivity testing tool, and let's run it 100 times. Make sure that when it says monitored primitives, you select the moose population, because we want to monitor the moose population over time. And for number of runs, put 100. And we can leave this confidence regions section as is. And I'd like to plot each run. When you're ready, hit run analysis, and you should get this nice looking figure that gives you a range of uncertainty about the future. This population could go extinct, and it could increase fairly dramatically. It's hard to know because the future is totally uncertain. And so this is kind of provides a way for us to account for, to embrace the uncertainty we have about the future. All right, and if you want, here, I'd like to see the spaghetti plot. Let's actually plot that. I think I must have accidentally unchecked the plot each run button. So let's run it again so that we can actually see the what I call the spaghetti plot. And this is where every plot is visible to you. So you have all 100 of your trajectories on the same plot, which is kind of nice, and it is a common visualization. So here we go. What I'd like you to do next, now the moose population right now is starting at a population size of 10. What I'd like you to do is change that all the way up to 500 and rerun the model. Rerun the model with the sensitivity testing, and I'd like you to answer the following question. Is the effect of demographic stochasticity, which is what this model is representing, is it bigger at high or low abundances? All right, so run it. We have already run the model using the sensitivity testing tool with an abundance of 10. Run it again with an abundance of 500, and respond in Web Campus about the difference between the low and the high starting abundances. What looks different? And the short answer question 4, is there any risk of extinction when the initial abundance is at 10? What about when it's at 500? So is there a difference in extinction risk when you start the population at a low population size, a low abundance, or a high abundance? And this ends up being super relevant to conservation biology. So take a minute to think about that, play around with the model, and answer the questions on Web Campus. Environmental stochasticity refers to the fact that we cannot predict whether next year or the year after that will be a good year or a bad year for the population. When we say good year or a bad year for the population, we mean, is the population going to be able to give birth to more individuals because the habitat is better, there's more resources, or maybe there's a drought and the population death rate goes up? That would be a bad year. So we can't predict necessarily what the future is going to look like for the weather or for the resources for this population. And that refers to what we call environmental stochasticity, that inability to predict the future, whether a year is going to be good or bad for the population. So we can, again, incorporate random numbers into our model and embrace this uncertainty we have about the future. Now, environmental stochasticity is in contrast to demographic stochasticity, which is what we looked at before. We can think of demographic stochasticity as individual level, inability to predict what's going to happen at the individual level. Is an individual going to die? Is it not? It doesn't require the birth rate or the death rate to change. It's just that we don't know at that individual level who's going to be successful, who's going to be unsuccessful. Whereas environmental stochasticity refers to those per capita vital rates, the birth rate, the death rate, the fractional death rate. Those are unpredictable as well. That's environmental stochasticity, when the birth rate and the death rate change year to year, and we can think of that as just based on environmental conditions. Are they good or are they unfavorable to the population in a given year? So let's load this link up. This is the last model that we'll be running before our more formal and more interesting PVA models. So I'd like to open in a new tab. We can look at it and clone it so that we can make changes to it. All right. And let's take a look at it. It should be running for, let's change it to run for 20 years. All right. And the birth rate should be at a mean of 0.5. And this is a random number generator. This is now, the birth rate's going to change year to year. So a random, we're going to use a normal distribution to allow the birth rate to go up, to be favorable one year, to be unfavorable the next year. And we're going to use this standard deviation term to be 0.3. All right. And now the death rate, we're going to have the mean be 0.4, just like we had before. The death rate was 40%. But now we're going to let it vary from year to year, and the variability is described by this standard deviation term, which we set at 0.3. So let's take a look at what happens if we run this model. All right, so that's one possibility. Let's run it again. Wow, it's a very different possibility. Now this one went extinct. So we're starting at a population size of 50 here, and we get to very, very different outcomes here. Let's move this to 10. So we start the initial population size at 10, and let's run the sensitivity testing tool and run it 100 times. We're monitoring the moose population, and we can keep the confidence regions the way they are. And I want to plot each run, all right? It just takes a minute to run. And we see the cloud of potential futures. So we're now interpreting a whole range of 100 times that we've ran this 20-year model, and this figure encapsulates all 100 runs. Sometimes in some runs the population got up to almost 500, and other times it went extinct. We can look at the spaghetti plot as well and see how variable this population really is. So I encourage you to play around with this model a little bit, and then to go answer the following questions on Web Campus. So first of all, I want you to change the initial abundance of this model to 500 and rerun the sensitivity testing tool and see what happens. Does the population level impact of environmental stochasticity depend on the initial abundance? If so, how? And finally, can you explain why populations with a restricted geographic range, that is, like a small island, why such populations would be more vulnerable to environmental stochasticity than populations with a large range? So try to think of reasons why an island, a small population that's restricted in its geographic range, might be more vulnerable to environmental stochasticity than populations with a very large geographic range. All right, so take a minute to record your answers on Web Campus. And I will return in the next lecture to start talking about the Grizzly PVA. But if you want to get some more information about any of these basic concepts of population modeling, feel free to read through all these extra materials at the end of the website. All right, I'll see you in the next